In this Back to Basics tutorial, we're going to take a look at those mysterious black and white maps that are at the heart of ForestPak's approach to scattering. In fact, understanding distribution maps can make getting the right results much easier and faster, as well as helping you to create your own custom patterns. They work based on one simple principle. A white pixel scatters an item, and a black pixel does not. This means that each pixel on a distribution map has basically two states. Either create an item or create a gap. The benefit of this system is that it's very easy to create specific patterns by drawing bitmaps in a photo editing application or even generating them procedurally. To illustrate how they work, let's look at a few examples. A solid white map will create a dense grid of items because every pixel is full white. This is useful for ground cover like grass where you want an unbroken blanket of vegetation. On the other hand, this noise map has a mixture of black and white dots to create a more chaotic distribution. Or you can even create regular patterns by laying out white pixels in a grid. This is useful for more man-made distributions like city grids, lighting, furniture, and much more. The built-in maps are positioned and scaled on a plane defined by the ForestPak's local XY axis. Unless you're using a surface in UV mode, in which case the surface's UVW coordinates are used instead. To change the size of a map, you use the density size settings. This sets the scale of the map in real-world units, and the map is then tiled in all directions. Remember that the perimeter of the scatter is always defined by the items in the areas list. The distribution map only defines the pattern for the scatter within these predefined areas. So as an optimization tip, it's helpful to know that ForestPak calculates every pixel in the map, whether it's black or white, it thinks about them all. Therefore, to increase the density of an object, it is more efficient to use a distribution map with more white pixels than it is to reduce the size of a map with a lot of black pixels. For example, using the dense map at a large size will yield similar results visually as using a sparse map with a small size, but in the last example, Forest has to process far more items because of the increased number of black pixels in the map. So, you can also place a map in the scene visually. To do this, click on Pick Start and click in the scene to specify the top left position of the map. Then click Pick End and click to place the bottom right. When Draw Gizmo Corners is enabled, you'll see crosses to help visualize where the map tiles. So now we know that a map size can be controlled using the density settings, but how many items can a distribution map actually scatter before it repeats? Well, for the built-in maps and textures loaded directly into the bitmap slot, ForestPak creates one item per pixel, if it's white of course. This means that the built-in maps, most of which are 100 by 100 pixel resolution, are capable of producing up to 10,000 trees in an area before the pattern repeats. Of course, if you use a higher resolution bitmap, it allows you to create many more trees before tiling occurs. For example, there are some new maps in ForestPak 6 whose resolution is 128 by 128 pixels. Therefore, these maps can create 16,384 trees before they tile. In addition to being scaled, maps can also be offset and rotated using the parameters with the same name. The white point, the value at which a pixel generates an item, can also be adjusted using the threshold parameter. At the default 50%, any pixel above mid-grey will create an item, and any pixel below 50% will not. We've included over 35 maps in ForestPak, but sometimes you'll also want to create your own. That's no problem. You can either load a texture directly into the bitmap input in the distribution rollout, or load a map, including procedural maps, into the map input. When using the map input though, there's a slight difference. The pixel settings become more important. Since procedural maps may be used in this slot, the pixel parameters allow you to set and specify a resolution, controlling exactly the number of items this map generates. So you'd use a low number for few items and a high number for more. Be aware though that if you're scattering on surfaces, then these settings behave slightly differently, depending on if you're using XY or UV mode. In surface XY mode, when using the built-in maps or a texture in the bitmap input, the density settings behave exactly the same as we've just seen. The surface's own UVWs don't actually affect the distribution. However, In Surface XY and Surface UV mode, when using a texture in the map input, the density size settings only change the density of items without affecting the position or the scale of the map itself. The Surface's UVWs are now responsible for placing the map, which acts as a kind of filter on top of a solid grid that's defined by the combination of the density and the pixel settings. So, for example, a pixel setting of 100 and a size of 100 centimeters will give the same results as a pixel setting of 200 and a size of 200 centimeters. This is because though the resolution was increased, so also was the size of the grid. In this mode, to offset, rotate or scale a distribution, you'd either have to modify the surface's UVWs or the map's coordinates. Finally, another thing to note. In Surface UV mode, when using the built-in maps or a texture in the bitmap input, the size settings scale the distribution map using the Surface's UVWs, not in world space, as a reference. The final distribution is therefore determined by a combination of the Surface's UVWs and the density size setting taken together. When manipulating distribution maps, you may occasionally get a message that the density of items has reached the max density limit. This value is there as a safety net to prevent you from accidentally creating so many items that it affects system performance. However, if you need more items, simply increase the max density value or enter 0 to remove the limit altogether. And that's more or less all you need to know about distribution maps. Stay tuned for more back to basics tutorials coming soon.